Alright, hello everybody. This week we're going to talk about dynamic routing. This is chapter 7. What we're going to talk about are going to be the dynamic routing protocols and the distance vector dynamic routing protocols. We'll also talk about RIP and RIP-NG, which is RIP is an older protocol, but it's still around. We'll talk about link state routing, and then finally what the routing table does for us. So this will be a little bit in contrast to last week where we talked about static routes. And if you'll remember from last week, I told you that you can add a static route to force data to go through a specific route on a network that's connected in multiple places. And there are many reasons to do that, but a primary one is for link cost. And by cost, we don't mean like money that actually changes hands, but we mean maybe one link is slower and it's only a backup. Maybe you've got 10 megabit links between everywhere, but because this one has to be up at all times, you've got a 56K backup link over here. So you set that cost higher, and that link will only be used if it becomes necessary. So we'll talk about the basic operation of dynamic routing protocols. We'll talk about static routing again so that you can compare it to dynamic routing. We'll talk about what networks are available during the initial discovery phase of a network. We'll also talk about the different categories of routing protocols. And this is where you can really get bogged down in this because there's so many different routing protocols that we'll just discuss. At this layer, it's important that you just be familiar with all of them and know that with the dynamic ones, as long as they're set up the same on your routers, you're pretty good to go. We'll talk about the types of the distance vector protocols as well, and then RIP and RIP-NG. And we'll talk about link state routing protocols and how they learn other networks. We'll also talk about a link state update and why it's important that those take place. We'll also talk about the advantages and disadvantages of those. And then we'll talk about link state protocols like OSPF and ISIS, which are the protocols that routers use to actually communicate with each other. We'll talk about administrative distance and metric again. We'll also talk about the concept of a parent-child with a routing table. And we'll look at IP4 and IP6 routing tables and how they're set up. Finally, we'll talk about how a route table is used to determine how to forward a packet. So dynamic routing has been around since the late 80s, and newer versions support IP6. Here, for example, is just a list of some of the different types of routing protocols. IP4 distance vectors you'll see like RIP, RIP-v2, and eGRIP. Link state protocols you'll see things like OSPF and ISIS. And for path vector you'll see things like BGP or your border gateway protocol. Now in this table they're showing that compared with IP6 as well, and you'll see that IP6, RIP-NG, or eGRIP for 6. OSPF3 supports 6. ISIS has an addition for 6. And border gateway is called border gateway MP for IP6. So the purpose of a dynamic routing protocol is to facilitate the exchange of routing information between routers. Basically, this includes discovery of remote networks, maintaining up-to-date routing information, choosing the best path, that's a really important one, and then the ability to find a new best path if the current best path is no longer available, or if for some reason the metric has been changed on it for it to have a higher cost. Basically, before dynamic routing protocols, all of these routes that were put into networks had to be assigned manually. And changing something on a network meant that you had to change everything, to make it work. So some of the main components of dynamic routing protocols are going to include things like data structures. These are going to be the tables or databases used. This is normally kept in RAM. On some really big routers, you may find they have hard drives that store this. They may have both. They may have a solid state hard drive that reads it into RAM when it's booted. They're also going to contain routing protocol messages. And these are basically the messages that are going to be used when the routers actually exchange information. Then finally, all of the different routing protocols are going to have some kind of algorithm they use to determine the best path. If things are being done automatically, then the best path needs to be automatic as well. So there's going to be some sort of algorithm that each of the different routing protocols are going to use to figure out how to compute that best route. Here we're just giving an example of that. And here we're looking at, for example, egrip. And they show that egrip maintains a neighbor and a topology table. So we have two routers in this picture. The first thing they're going to do is send an egrip hello to each other, followed by an update, a query, a reply, and then an acknowledgement. So advantages of dynamic routing are mainly that they can automatically share information about remote networks. If something on a network changes, they can use their algorithm to send that information to all the other routers using the same protocol. They are able to automatically determine the best path. Compared to static routing, because all of this is automated, there is much less administrative overhead in actually setting up the routes. And they help the network admin manage time-consuming processes like maintaining static routes. If you're a small network and you've only got 2 or 3 static routes, by all means, it's pretty easy to change. But let's say you've got 10 or 20,000 machines and 800 or 900 routes. Well, changing those becomes a big pain. Especially if you've got multiple routers you're going to need to change those on. The disadvantages, however, are that part of a router's resources have to be dedicated to maintaining the dynamic routing protocol. CPU time and network bandwidth are both going to be used for this, because for the routers to exchange information, they have to actually send that data over the pipe. And that means that part of your bandwidth is going to have to be used in sending information back and forth for the dynamic updates. And there are a few times when static routing is more appropriate for that reason. So something you're going to see in the real world is that networks typically use a combination of both static and dynamic routes. Static routes provide ease for routing table maintenance in smaller networks that aren't expected to grow. And they route to and from a stub network, which is a network with only one route and no knowledge of any remote networks. You pretty much have a stub network at home, even though you're using NAT. If you weren't using NAT, it would be a true stub. And your network doesn't connect to anything else but whatever ISP you're using. So your router doesn't need to know anything about routing to anywhere other than the computers that are on it, because it's going to ultimately have something like a gateway of last resort set that's going to send that data on and let the routing take place at the ISP and let them deal with it. And when accessing a single default router, that's used to represent a path to any network that does not have a match. That's again your gateway of last resort, so that's a static route. So here we've just got an example of that. You see dynamic versus static. We've got a couple of links to look at. Router 2 is connected to the other networks and to the internet. It is also my only way out. I just use a default static route to reach any network I don't know about. Because there's only those 2 networks and you can't go anywhere else, there's no reason for that machine to need to know anything else. So here they provide a static versus dynamic scorecard just to kind of give you some information on static routing. Advantages, again, easy to implement in a small network. It's very secure. That's important if you're dealing with something like a classified network, because no advertisements are sent as compared to dynamic routes. Now, I kind of jumped over that, but an advertisement means that a network is available. And with a dynamic routing protocol, when the new network is available, it will send out a route advertisement to tell those machines how to get to it, or tell those routers that it's there, who will then ultimately update their routing table saying, hey, look, this new network's available over here. In a static route, the routing destination is always the same. Packets are going to take the same route if it's statically assigned. And no routing algorithm is needed so that there aren't CPU uses there. The disadvantage, again, it's only suitable for small, simple networks. Configuration gets very complex as the network grows. And another disadvantage is that when traffic needs to be rerouted for some reason, it requires manual intervention. So here, looking at dynamic with a scorecard, we can say the advantages of dynamic is that it's suitable in all topologies where multiple routes are required. It's generally independent of the network size. Once you get it set up, you can grow. It's not that big a deal. And it automatically adapts to rerouting traffic when possible. It can be more complex to implement, however, and because of those router advertisements we talked about earlier, it's less secure. The route depends upon the current topology. And because these routing algorithms require CPU time and bandwidth, there's a cost associated with them. All right, so in general, when we talk about dynamic routing protocols, we can describe them as a process like this. First of all, your router is going to send and receive routing messages on its interfaces. It's going to share its routing information, or basically its table, with other routers using the same protocol. So there is where it's using the bandwidth. It's actually going to send those advertisements we were talking about to the other routers on the network. They're going to exchange routing information to learn about those remote networks. When a router detects a topology change, the routing protocol can advertise this change to the other routers. So when, if, for example, we have 3 links that are together, if one loses a link to another one, well, using a dynamic protocol, it's going to update all the routers in that link to say that that is down. And here we got an example of showing running RIP2, and this is a cold start. So this means that from down, what happens? So as these routers come up, first of all, router 1 is going to add the 10 dot network. And it's going to it's going to advertise that it can get to that network through Fast Ethernet 00. And that 10.2 is available through the serial interface. So then router 2 adds 10.2, and it shows that 10.3 is available through its serial interface. Router 3 finally is going to show that 10.3 is available, and that serial 01 gets to 10.4 through a fast Ethernet route. So now router 1 is going to send that update out the serial interface. And then router 2 is going to take that information and it's going to send it out to router 3. So ultimately, as this continues, a process is known at the end as convergent. Router 2 is going to send an update about 10.3 through its serial on to the next router. You see here the routing table is getting updated and the count is being added with a metric showing the number of hops, which is the number of routers it must go through to reach from one to the next. So finally, router 3 sends information the other way about the 10.4 network. And ultimately, I'm going through these kind of fast, but you'll see ultimately with them running RIP2, all of the tables are finally updated because they now all contain all of the routes available on this network. Now that's a small example, but that's actually what happens even on a larger scale. And ultimately, when that's finished, you have what is called convergence. And a converged network is one where all the routers have accurate information about the entire network. Convergence takes time, though, because all of these routes have to be updated when something changes before it's converged. They say that a network is not completely operable until the network has converged. Convergence properties include the speed of the routing information and the calculation of the optimal paths. And generally, with older protocols like RIP, they're slow to converge, whereas some of the more modern ones, eGRIP and OSPF, for example, converge more quickly. RIP, you'll find as we go on through this, is one of the first protocols that was around, and it updates relatively slow. So here we're looking at just a list of the classifications of some of the routing protocols on the dynamic side of things. And we've got interior and exterior as our first definitions. Your IGPs, your interior gateway protocols, are broken down into distance vector and link state. Distance vector contains RIP, iGRIP, and eGRIP. Link state are things like OSPF and IS. Then under your exterior, we have path vector routing, which are things like your border gateway protocols. So interior gateway protocols are used for routing within a single autonomous system, or AS. And these include RIP, eGRIP, OSPF, and IS. Exterior gateway protocols, though, can route between these AS, these autonomous or administrative system numbers, either way you want to put it. That is the official routing protocol used by the Internet. And the reason is everyone has their own autonomous networks on the Internet, but using a common protocol, they are able to converge at some point so that all the networks know how to get data to the other networks. I really shouldn't put it that way, because it's not like every single router on the Internet has a list of every route on the net, but they know where to send data if they don't have the route, up to a point that a link will be reached that does have that route to send it back down. So here we talk about the meaning of a distance vector. And distance is basically how far, and vector is direction. So for example here, these two routers are exactly one hop apart because there's only one link between them. So RIP1 was the first generation in its legacy. RIP2 is a simple distance protocol. iGRIP is one of the first Cisco proprietary ones, and it was finally replaced with eGRIP, which is an advanced version of iGRIP. So basically, distance vector protocols use routers as signposts along the path to the destination. These signposts point the way from the source to the destination, and they're not necessarily necessary if all the routers are using an identical map of the network. So again, there's where convergence comes into play. Here's an example of a link state protocol. We're dealing mainly with IPv4 at this point, so OSPF is a popular one, and IS is popular in provider networks, so your ISPs like to use that one. So classful routing protocols do not send subnet information along with their routing updates. Only RIP1 and iGRIP are classful. It is important to remember that's one of the reasons these are obsolete, is because we really don't run classful networking anymore. They were created when networks were located based on only those classes. So think back to your 101 days, your A, B, and C networks. They cannot provide for variable length subnets, so they cannot do CIDR. There is only classful routing with these two old protocols. So they create some problems in networks if they're used for that reason. Classless protocols include the subnet mask. So this is IS, OSPF, eGRIP, and RIPv2. Because they include the subnet mask, they are capable of doing CIDR and variable length subnet masks. And because they also were updated, they include routing for IPv6 protocols. So here is a great little table of some of the different types of protocols there are for routers, and just some pros and cons to each of them. You see here, for example, RIP v2 is slow to converge, but it's very low on network resources. IS, on the other hand, is very fast to converge, but it's kind of high on the resources that it needs on a router. So you need a router with a good bit of CPU and memory to handle something like that. So when we talk about routers, we talk about metrics. And a metric is a measurable value that is assigned to a route based on the usefulness of that route. It is used to determine what is called the overall cost of a route. Routing protocols determine the best path based on the route with the lowest cost. So distance vector protocols are going to share the updates between neighbors, but they're not going to be aware of the network topology. They send updates to the broadcast IP of 255 all the way across the board, even if the topology has not changed. The thing about these protocols is they send the update whether it's needed or not. And the reason for that is to make sure that if a new router is put on, it's going to get it. These updates consume bandwidth and network device CPU resources. RIP and eGRIP use multicast addresses for this. And eGRIP will only send an update when the topology has changed, unlike RIP that's going to send it regardless. So here we've got just another example of a distance vector algorithm. And we see that we're talking about RIP here. And RIP uses something called the Bellman-Ford algorithm as its routing algorithm. iGRIP and eGRIP, however, use one that was developed by Cisco called the diffusing update algorithm. So here we've got an example of showing that we're doing routing updates broadcast every 30 seconds. Updates use UDP port 520 with RIP. And with RIP2, they're sent out a multicast address. So you see we've got that 224 address. RIP-NG is based on RIP2 with a 15 hop limitation and an administrative distance of 20. So RIP-NG, again, remember, was added so that we could get IP6. eGRIP is bound to triggered updates, and it uses what's called a hello keep alive. A hello keep alive is just a packet sent out very much like a ping between routers. It sends a hello and waits for a yes, I'm there. It maintains a topology table based off of that, and it supports rapid convergence because of that. iGRIP again uses that single 255 broadcast address, but eGRIP over here we've got on a multicast address. So here we're talking about how to enable the RIP protocol. So first we're going to do a conf T to get into our configuration mode. Then we're going to type router RIP, and then we're going to tell it what networks we have. Network, in this case, 192.168.1 and then .2. So here we can do show IP protocols, and it'll show that our routing protocol is RIP. Then we see that we've got information on our route. We're sending updates every 13 seconds. The next one in this case is due in 16. Here they're just showing with two different routers how to look at it, and we're looking at RIP2 over here as well. To do RIP version 2, we do a router RIP command and then say version space 2. Similarly to RIP1, RIP2 automatically summarizes networks at major network boundaries by default. To modify RIP2 to not do that, you need to do the no auto summary router command. This command has no effect on RIP1, however. When automatic summarization has been disabled, RIP2 no longer summarizes networks to their classful address. So now instead it's going to send every subnet out with its IP updates, or its route updates. And the show IP protocols now states that summarization is off. So here we should be able to see that. Basically, the reason for that would be to stop sending the unneeded updates that are wasting bandwidth and could be a security risk. But now that we've turned them off, if things change, we're going to have to make manual changes. So here we're showing the gateway of last resort is set. So this tells us that in this case, 209.165.200.226 is our network 0000. So that's our gateway of last resort. Here to advertise IP6, what we have to do is do an IPv6 command and say unicast routing. Then we need to turn it on, so we go to the interface, IPv6 RIP, and then here they're doing RIP AS enable, which is going to be your advertising. And then exit, and then finally issue a no shutdown so that interface will stay up. If I do a show IPv6 protocols, I should see that RIP is turned on in this case. And show IPv6 route ought to show me the routes that I have running IP6. So here we can look at it again. So other protocols that we have are the link state protocols, and if you'll remember, they include OSPF and IS. And they use something called Jastraka's algorithm. I've never been able to say this person's name. But the shortest path in this case is reached by using metrics that include things like the bandwidth and the time it takes for pings to happen. So here we've got a network that's connected. If you look, we've got 4 routers each connected to 2 others, then one in the middle that's connected to 2 separate networks. And our administrative distances are listed here. So essentially what will happen is that this far link between R1 and R4 will be ignored unless the link between R1, R3, and R4 goes down, because our administrative distances here are smaller. So in one of these, each router learns about each of its own directly connected networks. Each router is responsible for sending the hello to its neighbors on those directly connected networks. And each router builds what's called a link state packet containing the state of each directly connected network. These LSPs are sent to all the neighbors who store all the ones received in a database. And then each router uses its database to construct a complete map of the topology and all the computers for the best path to each destination network. So in this case, you've got a topology on each of the systems, each of the routers. So here we're seeing the first step is to show that link state routing process is that each router learns its own links and its own directly connected networks. So step 1 on link 1 is going to be to learn about the 10.1 network. And over here it's going to be to learn about 10.2. So the second step is to, for each network, a router to, as they say here, meet its neighbors on directly connected networks. That means those routers are going to start exchanging with these hello packets. So the third step is for each of these routers to build the LSP containing the state of each network. So here, R1 says it's up, the cost is 2. R2 is a serial, the cost is 20. R1 to R3 is a serial with a cost of 5, and R1 to R4 is again serial, also with a cost of 20. So finally, once we've built these LSPs, we flood the network with them. And we do that by each router flooding that LSP to all of its neighbors, who are going to restore that in their own databases. And then the final step will be to take that LSP from each router and construct a complete map of the network. So now each of the devices on this network are going to know where each of the devices are outside. And here they're showing that again with the SPF tree. So the results are basically the destination, the shortest path, and the cost. So looking at this, if router 1 wants to get to 4, you'll see that it has a route to do so. And again, if we look at the routing table, it'll tell me who is directly connected, and it'll also tell me my remotes with what interface to send that data out and what cost that data is going to have. So a question that often gets asked is, why use link state protocols? Well, because each router builds its own map to determine the shortest path, the immediate flooding of these LSPs means there is faster convergence. LSPs are only sent when there is a change and only contain the information regarding that change. So once a network has converged, we're not going to send all that data again. We're only going to send what has changed between the connections. Some disadvantages, however, are that they maintain a link state database, and the SPF tree requires a lot of memory. This is extra things that have got to go into a router, so you need a bigger router to do it. The SPF algorithm requires CPU time as well, and a certain amount of bandwidth is going to be used with that flooding. That LSP flooding is going to take up time on your network. So here you see that we can create areas to minimize router resource usage. And here we've got what look like 3 different network areas. And what will happen is those routers that are between areas are going to run a different protocol. And that means that the links inside are only going to know about their own autonomous network. So area 1, these 5 routers in area 1 are all going to know about each other. But all of them except this router here between these clouds, as they're showing the areas, this will be the only one that knows about area 0. Basically, the rest of these will just think that their gateway of last resort is this router. And from that, they'll have to, it'll send it out to figure it out. So there are only 2 of these link state protocols. Open Shortest Path First, or OSPF, which is now up to version 3, which has support for IP6. And then IS, and IS was developed by the ISO. Here we can just show the IP route, and this shows us that we've got a network and what's connected. Directly connected entities on our network will show as directly connected if you read the table. So here's how to actually read that. The first letter tells us the root source. Next is the destination network, and then the CIDR notation, followed by the metric, then via how to get there, what hop, the timestamp, and what interface that should go out. So looking at your table, that's how to read it. So routes are discussed in terms of an ultimate route, a level 1 parent, or a level 2 child. An ultimate route is a routing entry that contains either the next hop IP or an exit interface. Directly connected, dynamically learned, and link are ultimate routes. So basically your exit interface is an ultimate route. A level 1 route here you see is a network that can lead to an ultimate route through an interface. So here we've got another level 1. Then a level 2 child route is a route that goes to a level 1 route. So here we've got kind of the route lookup process. If the best match is a level 1 ultimate route, then the route is used to forward the packet. If the best match is a level 1 parent route, it proceeds to the next step. The router then examines the child routes for the best path match. If there is a match with a level 2 route, that subnet is used to forward the package. If there's not, it proceeds and continues to search the level 1 supernet routes for a match. If there is a lesser match with a level 1 supernet, that route is used to forward the packet. If there is not a match with any route on the routing table, the router drops the packet. This is why the gateway of last resort is important, because if we reach all the way down to step 8 in this process and we don't have anywhere to send it, then ultimately we're just going to drop the packet. However, if I've defined that 0000 route, I'm good to go. So here we've got the best route is the longest match. So in thinking about IP6 routing, it's very similar, except the routes are going to be, a lot longer and the IPs are different. IP6 never was designed with classful routing in mind. It's always been classless. So the routes are all effectively level 1 ultimate routes. There are no level 1 parent and level 2 child routes. And here, just to give you an idea, we can do a show IP6 route, and it gives me a list of my tables. Again, the root source, then I've got a directly connected network, a metric, your interface, your administrative distance, and then ultimately how to get to that network. So what interface? Here we're seeing the end of it. The next hop and then the outgoing interface. So that is a quick rundown in Chapter 7. So what we've talked about, we've got routers that can automatically learn about other networks. We talked about how that happens with discovery. The best choice for large networks, is dynamic, but stouting is better for stub, or static routing is better for a stub network. They can be either classful or classless, but remember, everything we do now is classless. So you basically just need to know about classful so that you understand it. Your dynamic routing protocols, a link state is used to create a complete view of the topology. Metrics are used to determine the best path. Different routing protocols will use different metrics. That might include hops, delay, reliability, load. There's all kinds of metrics that can be used. Your show IP is going to show your table. Cisco routers use the administrative distance to determine what routing source to use. An OSPF link is an interface on a router. Information about that link is known as the link state. Link state routing protocols apply Distraka's algorithm, again I still can't say that, to calculate the best path when the accumulated costs are added together. And that is a basic rundown of Chapter 7.